Yesterday we talked about power models, where it was y equals ax to the p, where we kind of guessed what p was, if it was squared or cubed, and we kind of had to figure it out. So you could either take x to the pth, comma y, or x, comma the pth root of y. Both did the same thing. Now, to achieve linearity from a power model, we can apply logarithms. This way it's a little bit more set. A power model has the form y equals ax to the p. A and p are constants. Well, if we take the log of both sides, we get the log of y equals the log of axp. Then using our rules of logarithms, we can split up a and x to the p by the addition rule. And then we can bring the exponent p into the coefficient of log of x. So log of y equals log of a plus p log of x. And now there's a linear relationship between log x and log y. So for a power model, log x and log y are linear. And that p is the slope of the straight line that links those two logs. So we don't have to guess at it. We don't have to figure out, is this squared, is this cubed? We're given it now when we do our linear regression. And we can use the least squares regression line to transform data and get the rest of our information and to predict other y values or x values. So July 31st, 2005, a team of astronomers announced that they had discovered what appeared to be a new planet. They called it UB313. The potential planet is bigger than Pluto and has an average distance of 9.5 billion miles from the Sun. Could this new astronomical body, now called Eris, be a new planet? Well, what we're going to compare it to is the distance from the Sun in astronomical units. So an astronomical unit is the number of Earth distances the object is from the Sun. So obviously the Earth is one Earth distance from the Sun, and we use that as reference for all the others. Then how long it takes to go around, or how long it goes around the rotation in 1 Earth year. So we have these numbers. If you look at the graph, it's kind of a curved pattern. So we need to straighten it out. And instead of trying to guess what our p-value is, we're going to do the logarithmic way of doing it. So if we just look at the logarithmic, natural log of percent, or period, versus distance, we still have a curved pattern. And this would be linear if this was exponential. But it's not. So if we look at the natural log of distance and the natural log of the period, it is linear. Very good line. So it's linear and it is a power model. So it's just a step further than what we did yesterday. And that's what I just said. So when we do the Minitab output of the linear regression of the natural log of distance versus the natural log of the period, we get an R squared of 100%. It is perfect. So we have this perfect distance, this perfect relationship. We also have our y-intercept and our slope. And our slope is really what our power would be. So it's about 1.5, ax to the 1.5. But this is what it looks like. The natural log of the period, hat, equals our y-intercept, 0.0002544, plus 1.49986 times the natural log of distance. Now we want to see if Eris fits this model. If it fits this model, maybe it's a planet. So we have to put it into terms of astronomical units. So it's 9.5 billion years away, divided by 93 million years away, which is the distance the Earth is from the Sun. So we plug in 102.15, and for the distance, that's how many astronomical units it is from the sun. And when we calculate this whole right side here, it turns out to be 6.939. So we really have the natural log of the period, hat, equals 6.939. So that's the same as saying log base E of the period equals 6.939. And if you remember, we can change the base E to this number equals the period. So the period hat equals E to the 6.939, which is approximately 1,032 years. Now we have a residual plot for our natural logs of distance and natural log of period. Now we kind of have a pattern, but if we were to predict it, the distance is 6.9 something something something, so it would be over here. Actually, probably a little farther over. So it's above what we predicted. Or it's below what we would have predicted. So our prediction would be too low. So an exponential model of the form y equals abx can be done into logarithms. The exponential model. Take the log of both sides, split it up using our addition, and then using the exponent as the coefficient. So if two variables are related by an exponential model, a power model, then this relationship is true. So now one of the founders of Intel Corporation predicted in 1965 that the number of transistors on an integrated circuit chip would double every 18 months. Thought it would grow that much. This is Moore's law. One way to measure the revolution in computing. So here's our data. Here's our graph. If we just graph years since 1970 and the number of transistors. So very low, very low, very low, then it takes off, it skyrockets, it looks exponential. So if it's exponential, we just take the natural log of one of these. And that's what we did here. Years since 1970, still the same as it was before, and then the natural log of transistors. Either log base 10 or log base E, which is natural log, it doesn't really matter. So we can use an exponential model on this because x comma natural log of y is roughly linear. Look at it, you can kind of tell that there's a pretty good straight line there, maybe a little bit better than the one I drew. So it has a fairly linear pattern, so an exponential model, it makes sense here. We do the Minitab output, our r squared is 98.9, that's pretty darn good. We have our constant, our slope, so there's our equation. 7.0647 plus 0.36583 times the years since 1970, so not just years, but years since 1970, equals the natural log of transistors, because this is exponential. It's not a power model, it's exponential. So now we're going to use that to predict the number of transistors on an Intel computer chip in 2020. Well, 2020 is 50 years since 1970. So we're going to plug in 50 there. And when we figure out this right side, natural log of the transistors equals to 25.3562. That's what we have here, which is log base E of the transistors equals 25.3562, or E to that number equals the predicted transistors, which is what we're finding here. So about 1.028 times 10 to the 11th. It's about 100 billion transistors in 2020 is what we predict. Residual plot for the years since 1970 and the natural log of the transistors is listed here. What does the graph tell you about the appropriateness of the model? There's somewhat of a pattern, but the residuals go positive to positive as we move from left to right, but the residuals are small in size. They're not far off. So we still feel comfortable that this is a linear model using natural log of transistors versus years since 1970. And that's what we've learned in this section.